Our next speaker is Rohini, great friend. She has declared that to be a boson, but not yet Higgs. So she will defend. What next?
So it really sort of gives me a great pleasure to be here today to speak in the 50th year celebrations of math science. Math science, I am a bit older than math science, in fact, but it's much older than my life. I mean, it was a very established institute when I was born in science. And since I've been born in science, I've known this institute. I have had friends, colleagues, seniors, and have been coming here for many years. So it's a particular pleasure to talk to you all. So I decided that I will talk today about, we have found a boson, what next? So we have heard now two talks giving you the theory of the Higgs boson, problems or rather special features of a theory of scalars that Ramesh told you. Then we have had two excellent summaries of all the experimental results we have had. So in some sense, what I have to say covers most of this, which means that I have advantage, and perhaps even the students might think it's too simple, but then that's just my limitation. So what do I want to talk about? I want to cover three things. First, I want to talk a little bit about before the Higgs Independence Day, so to say. So that is a bit of a history where Professor Kibble left. Then I want to sort of not discuss in too much detail because there will be one more talk in the next days. Do we know it's a Higgs boson? It's a boson for sure. Do we know it's a Higgs boson, a Higgs boson? And then the next question comes, whether it is the Higgs boson. And if it is so, then what? What can we learn about the standard model and the beyond standard model from the information that we already have on the mass of the boson that we have seen and on the rates of its production? So these are the three things that I wish to cover. As I said, I really begin at the beginning almost. This is the 1967 paper of Steven Weinberg, which was called Model of Weak Interactions of the Leptons, which in fact ended up finally being the gauge theory of weak interactions. And particle physicists called it a model for a long time. Now also we call it the standard model. But indeed, it is the theory, gauge theory of weak interactions and electromagnetic interactions. And it used the Higgs mechanism, which was explained so beautifully this morning's talk by Professor Kibble. But I think we must remember that this was only one way of breaking the symmetry, and it was likely, though not probable necessarily, that the model was right and still there would not have been any Higgs. I'm talking about 1967. Now, in between, that when it was proposed, we only knew perhaps U, D and S. And this theory, when extended to include quarks, predicted the existence of a fourth quark, which was the charm quark, and demanding that the theory explain the observed phenomena of oscillations of K0 and K0 bar and calculate the mixing correctly in terms of some diagrams, predicted actually the mass of the charm quark. Of course, the calculation wouldn't have made any sense if the theory was not renormalizable, because then there was no sense in calculating loops. But in fact, in 1971, there was this seminal paper where Townsend and Weinberg actually proved the renormalizability of the electroweak interactions when the symmetry is broken spontaneously via the Higgs mechanism. So this is at the level where theorists would have been very happy. But in 1974, there happened a very particular discovery, which was almost by chance. And I guess at this point I can say that I actually began my graduate physics career in the 1974, the year of November Revolution. So in some sense I am a child of gauge theory days, and I think I am representative of the whole lot of physicists, phenomenologists, theorists, experimentalists who lived in this 40-year-old period. So in this experiment, people found evidence for the charm quark, more or less at the mass that was thought of. and also one had found evidence for the weak neutral currents, and this basically galvanized the interest in gauge theory of weak interaction with spontaneously broken symmetry with the Higgs. And in 1976, four very eminent physicists, including John Ellis and Marie Gagarin, Nanopolis, and I forget the fourth name, they wrote a very long article on nuclear physics B, which was called Profile of the Higgs, but it's quite amusing that the footnote or somewhere there was a sentence which said, this doesn't mean that we necessarily believe this exists. So this is the character, okay, but at the same time, as I said, the phenomenologists had started suggesting ways and means of ascertaining whether the Higgs boson really exists. Now this is just to remind myself also that this was actually the first single author paper that I wrote as a graduate student, and in fact it says trymuon events due to neutrino and antineutrino production of Higgs bosons. And what I had calculated was a famous vector boson fusion diagram which now we very merrily discuss at the NLC, except the Higgs boson mass that I had used was 1.5 GeV. Alright. Now on 4th July 2012, we got this beautiful, this and many other events were presented by CMS collaboration. Now here is the point where all of us merrily call it a boson. We call it a boson because this is the telltale signature of a particle decaying into two photons. That is the first point. Second one, which I have picked up from Atlas, which also is the same thing, except that it's a Higgs decaying into two Z bosons, and each of the Z decaying into a pair of lepton and antilepton. So there is a resonance which decays into two identical spin 1 particles. So in spite of however agnostic you may be, once you see this, you cannot deny the fact that you have seen a boson. So that is the reason. This was of course the, I should also say that I will show very few experimental plots because we have seen them in Kajari's talk and a much better and much more recent ones. But this is just, I'm not going to discuss this in great detail. I'm just flashing them by. So there was this gamma gamma and there was this ZZ. The veteran also had a 3 sigma result in BB bar, and now LHC has signals in WW and as well as in tau tau. Now for most of the discussion, whatever I will discuss, I will actually concentrate on the information that we can get from the fact that the Higgs decays into 2 photons, 2 Zs, 2 Ws. Most of the things, that's what I will use very often because that's what we have right now got enough information on. So beginning in 1978 from calculating vector, as soon as this signal was announced, this is just one of the many papers that came. Luckily for me, I feel very happy that it came in the same issue of Physics Latest B that announced the discovery, and immediately all of us jumped upon this one number that the experimentalists have provided and started asking the question, is it standard model? Is it something beyond standard model? And I want to convey some sense of some of the points that go into these discussions. And I must say here that I am a very representative member of the entire particle physics community which has lived in this period. So most of us, our horizon has been bounded almost by the Higgs boson, the theoretical problems that it creates, the new ideas of physics that have come from that. And since that is the fulcrum, it's not surprising that with this one number, with this one discovery, we are already able to say a lot about what may or may not lie ahead, and some of our favorite theories are, if not dead, are already in the hospital. Okay? All right. So, the periodic table of particle physics and interaction has arrived. Before 4th of July, it was almost complete. We had Fouriers, which I'm not even showing because we had a big talk and nice talk on that. Then there were these bosons, which we knew, and we always said, oh, the bosons are force carriers. Everything changed on 4th of July, and you will notice I removed the force carriers because Higgs does more things than that. And what do we know about this boson that we found? We know that it has a mass between 125 and 127, depending on the mode, depending on the day, depending on the flavor of your experiment. So it's somewhere around there. It's certainly electric charge 0, and it's certainly not spin equal to 1. That is definitely what we know. Now, so as I said, this one fact we know already. It has integral spin. We also know that it is not spin 1. Now actually, beyond this, so far I can say things using just quantum mechanics. Now if I want to say something more, then I need to use my knowledge about what we expected Higgs boson to do. So if you look at the number of events which are contain gamma gamma and number of events in ZZ channel, which I'm sure Kajiri showed you today, and if you compare the relative rates of gamma gamma to ZZ, the production rate is an immaterial thing. You only are comparing the branching ratios of the Higgs to gamma gamma to Higgs to ZZ. And right now what we say, indeed it's consistent with the fact that H to ZZ is a tree-level decay and H to gamma gamma is a loop-induced decay. This is actually something very simple that one can do a small exercise. But having done this exercise, now you immediately can draw a very important conclusion. Given the fact that you have a resonance which couples to two Z bosons at the tree level, it immediately falls out that this guy, whatever is being produced, is dominantly a CP even character. Okay, the dominant part of the coupling is CP even. This just follows from the relative rates, and now the analysis of the angular distributions of the decay leptons in Higgs to ZZ to 4 leptons mildly begins to support even the spin zero interpretation. So this is what experiments have more or less told us. Actually something even further, now the fact that you have observed the Higgs into the 2W channel, in fact the observation itself to get rid of the standard model WW background, it crucially uses the fact that if it is the Higgs, it's a spin zero object decaying into two spin 1 particles. And then there are specific angular correlations if it's a spin zero object. So this is again angular momentum addition. You're not doing much more than that. And therefore, you know from the fact that the rate of the ZWW channel is more or less compatible with the ZZ channel as expected in the standard model, you already know that this says that it's a strong indication against spin 2. But that's just an indication, we don't have a measurement. Clearly a lot of work is going on, a lot of is required, and I'm just sort of put a few papers, but there is one paper on the net, where 2 papers on the net every week on the subject. So what do we have? We have mass and rates in many different channels. Plus we also know that there is no standard model light state till about 600 GeV other than this one state that we have seen. And the production cross sections for any other heavier state now have been limited to the level of 0.3 times standard model cross section. What does it mean? It means that if I am thinking of a supersymmetric theory, if I am thinking of additional Higgses, this is a piece of information that I should keep in my mind in trying to understand and interpret. So, what experimentalists do give us is what they call signal strength. Now here I like to warn my theory colleagues, because this is something I also learned only sort of at the time the Higgs discovery was announced, a little bit before that even though this is presented as signal rate, what this is, please note, there is a hat on top of it, mu hat. So that's the optimal value of the signal rate that gave the best possible significance for the signal. So if you are going to interpret that as actual rate of observed cross section to the standard model prediction, that's only an estimator of that value. The errors in that sense as a ratio of cross sections is something that we will still need to wait a little longer before we know it. So this is just for us who getting excited when we see that maybe gamma gamma has twice the rate of standard model. We should go back and realize that this is what we are getting. So this is what Atlas told us, that in the gamma gamma channel they seem to see a signal strength which is larger, which is, I've been told now that perhaps it may not be so as high as this, but on the whole there is some large rates. This is a summary slide which I have taken from the early results that were published in by these two collaborations. I have not updated it for HCP, but the gamma rates certainly have not been updated as yet. In the tau has shifted a bit better, and so this is really what we have. Now, what do we know? The couplings to WW, ZZ and TT bar of this resonance seem to match the standard model expectation. See, there is one lesson in spite of my warnings that we can take, is that the fact that most of the numbers are around 1, because you are producing the Higgs through glue channel. Glue channel production is only through TT bar loop. The decays of the Higgs into gamma are again through TT bar loop. So even if you have not seen the fermion coupling directly to the top, indirectly you have seen it. And if it is the Higgs, its dominant couplings are to WW, ZZ and TT bar, the largest couplings. So right now the data seem to tell us that this resonance seems to have couplings which are more or less matching the standard model expectations. And Sabatron has provided us some evidence for the BB bar coupling. Clearly, right after the result was announced, I am not going to go through even the titles of these papers. I have not even tried to list all the papers. This is just to tell you that there are many facets of this result which is being looked at from many different angles, and whatever I have written in blue are the papers which I would try to pick up to tell you a few facts about. Okay? So there were a large number of different papers which have been coming and which have come, and for example what they are trying to do is trying to analyze, is there space for anomalous Higgs coupling, is this a Higgs or is this some imposter, is this, how can I analyze it in an effective theory approach where I pretend that I don't know anything about standard model, can I see, is there any space for, is there a space for some of the realization of the light composite Higgses, so on and so forth. And in fact, before the discovery was announced in January 2012, some of us had come up in Lesuge together and made a report on connection between the Higgs and the BSN before the discovery was announced, and a lot of things were discussed in this report, and I will try to pick up few things from here and there in this. So what are the questions that we want to now answer? Is it, as I said, is it a Higgs? Now what is meant by saying that is it a Higgs? What it means is this a boson that in fact has couplings to the fermions, two-level couplings to the fermions, electroweak gauge bosons which are proportional to their masses, and loop-induced couplings to gamma and GG induced through a TT bar loop where the coupling to the top is proportional to its mass. If it is so, then the resonance we have seen is a Higgs. I am sure that you would have heard in Kajari's talk that the CMS fits that are being made more or less seem to say it looks like a Higgs. So it's a bit like Superman, it looks like a bird, it flies like a plane, and for all we know it's a Superman. We don't know that. So that's the question we want to answer. Okay? But right now it certainly looks so, and it will be discussed in quite a bit detail by Vishwaroop. Now I want to ask the second question. If it is a Higgs, what do I need to see if this is the standard model scalar or the imposter? Which means I have to determine the spin and the CP. Till I can say statements about spin and CP, I cannot tell whether this is the standard model scalar or not. Because it could be, for example, the pseudo-scalar that supersymmetric theories have. Could have been. We don't know, but now that we see it decaying into ZZ, I already told you that most likely that's not the case. But I'm just giving it for the sake of arguments. But as a general question, you would say how to determine the tensor structure of the interaction of this resonance with a pair of fermions and gauge bosons. That's a general question that you ask, and you kind of try to answer this question in all generality, and now you see with the more data and more techniques that you have got, can you answer this question in a kind of model independent way? Okay? So which means that then you try to use a single channel. See, right now I made arguments by saying I compare the gamma with ZZ, etc. But now if I want to make a model independent way, I would like to see if I can use a single channel and get an answer to this question. This is a very active area of investigation. And then the last and not the least is assuming that this is the Higgs, what are the theoretical implications of the observed mass and on the observed rates. And it's amazing how rich the phenomenology of just the mass of the Higgs is. So that is the one thing that I would like to try to tell you. And this I will discuss the BSM physics, what are the implications of this Higgs mass, the standard model, for SUSY and for heavy fermions. These are the three things I would like to cover. So let's remind ourselves what were the standard model predictions. The standard model scalar consisted of the completely proven gauge sector and yet to be completely proved scalar sector, but now we have really quite a lot of proof, but still we like to be more certain. So this is the scalar part of the Lagrangian, which after symmetry breaking in terms of, this is the doublet, the SU2L doublet, and after symmetry breaking, when the neutral part T3 equal to half minus half component got a vacuum expectation value, this is the physical degree of freedom, and this guy has reduced to this term in the potential where V of h is lambda VH cube plus lambda by 4th h fourth, and here I want you to remember that MH is actually, if you remember, related to lambda and the vacuum expectation value V. So this is something that I would like you to keep in mind. What do we else we know? As I said, we know J should be 0, it's a CP even, it should have hypercharge Y equal to 1, and it should be a SU2L doublet. The tree level couplings are proportional to the masses, couplings to GG and gamma gamma are loop induced. When we have done all this, we will say we have a standard scalar. To remind you how, again, what do I mean by saying that you want to determine the spin CP in a model independent way, is we would like to establish, for example, what are the couplings, for example, of the Higgs to a pair of gauge bosons. This is the most general form that I can write using simple Lorentz invariance. In the standard model, I know A is equal to 1, and the coupling is only this first term. If I find some evidence, or if I can discriminate from the observed observations against B and C being different, being 0 or against, I would have determined the coupling structure in a sort of in a model independent way, and I would have understood and established whether the CP is indeed 0 plus plus, because if it is 0, if C is non-zero, then I know that there is some 0 minus component in my Higgs. Okay? And this, of course, I think is something that in the current of the parallel symmetry in the universe is still lacking. So these are three observational facts which cry out for beyond standard model physics, because standard model just does not have an answer to these three things. On the other hand, as a theorist, if I may ask what are the reasons for thinking that there is physics beyond standard model, most of us will actually list completely different 4 points, which is what were ably discussed by Ramesh today. First is the instability of the electroweak scale under radiative correction. This was also mentioned by Mariana. We need to get a basic understanding of the favor issue, what are the masses they are, the unification of the coupling, and inclusion of gravity in the picture. So as a theorist, we think these are the reasons for going beyond standard model. Observationally, these are the 3 facts. And as it happens, right now, supersymmetry happens to be one structure which was introduced to handle these issues, and which somehow very easily provides answers to these 3 above. And therefore, it's not a surprise that first we found the Higgs, we tried to see what, if anything, Higgs will tell us, or this boson will tell us about supersymmetry or otherwise. So I think I will skip this because this was really discussed very, very well by Ramesh, but maybe I will remind you briefly what was really happening is that the correction to the Higgs mass coming from the top loop, which is something that you can compute rather easily, is something like 0.2 times the lambda square, and if I want the Higgs, now we know that the boson is 125 GeV, which means I know that the correction that is coming from the loop should not be much more than that. So if I demand that the correction is at the most of the order of the Higgs mass, which is the physical mass that we have observed, then we know that lambda should be of the order of TeV. So this is really the name of the game, that supersymmetry keeps the Higgs light naturally, But if it has to do it naturally, then the scale of physics should be 1 TeV. This is basically the issue. Now, at LHC we seem to have found the light Higgs, 125 GeV, but we have no evidence, not just for supersymmetric, but for any BSM scenario. So, that is really the point. And therefore, now we think that the mass and the couplings of this light state may be the only thing through which we might get a view of the BSM till the 14 TeV or 13 TeV machine comes on, and we can try to understand these results and try to think what we should see or not see or check at the 13 TeV machine. So that's the focus of the phenomenology for most of the people who are looking at the data and trying to see what do these data tell me about fundamental theories. So before I sort of go on, I wanted to, I showed you the front page of one of the papers we read. Okay. And that has to do with this, that earlier there was a lot of excitement that both the collaborations had reported an enhancement rate, enhanced two-photon rate, and most of the theories clearly were extremely exciting. Okay, this we found very exciting, and this was indeed exciting because it is precisely the Higgs to gamma glue and Higgs to gamma gamma couplings that are loop induced, and therefore they are related, or they have the memory of the physics that may lie at a higher scale. That's actually the whole point. It is the chiral fermions, for example, which give a non-decoupling contributions to Higgs GG and Higgs gamma gamma. So these were the two vertices that we all were hoping might be different from standard model. So we were all sort of beginning to get very excited, but we actually that time pointed out that even if we need to first sort of look at it critically, whether this excess is just not due to uncertainties in our theory predictions that we have in the production rates. And indeed, precision predictions for the Higgs production was something that a whole lot of group theories worked together and put their predictions together here, and you can see this shows you the production predictions for the production of the Higgs as a function of the mass, and at 125 GeV, you rather say glue to Higgs seems to be rather well predicted. Okay, very good. Yes, indeed it is well predicted. What do the spread comes from? It comes from the fact that QCD has an inherent dependence on the scale. Even if when you do NNLO calculations and do the really a gigantic exercise, you still have a leftover dependence. There is a dependence on the partner densities which you use, as well as the knowledge of alpha s. And the LHC cross-section working group had in fact said that we should add them linearly because these errors have no statistical origin. These are just theoretical systematic errors, if you wish. And there are also some more approximations that we make in our calculations at NNLO particularly, which are due to the limitations of the effective field theory approximation, where the whole top loop is sort of compressed to one point. That's a heavy top mass limit calculation. So for 7 and 8 TeV, everybody sort of agrees that the PDF plus alpha s and scale uncertainty are about 10% each. Now, so the total theory uncertainties, if you add them linearly, are about 20%. In the experimental analysis in the early days, what they did, they said that the total uncertainty, they treated this uncertainty as Gaussian errors, and they added them, and then they said that experimental error was about 30% and the PDF was 10%. If I calculate the total error, it will be 33%, which means that basically we have not taken into account the theory error at all. So therefore, if we do this small exercise, add the error in linear instead of quadrature, what we here I show is RH to gamma gamma and RH to ZZ, okay, to the standard model is the same sigma observed over sigma Sm, and what we see is that if we take into account the errors added linearly, just look at this blue, that is enough, yellow, that is enough right now. So these were the numbers that I had written in the slide, R gamma gamma being here much larger, right? This is what I had written, but now if you see, if this is the error theory error, then what was quoted as a 2 sigma excess already reduces to almost 1 sigma excess. If you look at the sum here added together, weighted, the errors weighted appropriately. So what one is showing here is that, let's be careful. Before we start producing many models and talk about how I can increase Higgs to gamma gamma by introducing 20 leptons, vector leptons and what have you, let's step back for a minute. And not for a very, I should say for a good reason, because it's rather difficult to increase Higgs to gamma gamma. In fact, as I will try to come in the end. For discovery, perhaps this whole thing was not very relevant. I think these objections we are taking do not actually matter at all. But for the studies of the couplings, unless we use ratios of ratios or ratios of different observed rates, a discussion of how these errors should be treated in the extraction of the couplings is a very important one, and that will actually keep us all busy to understand exactly what do these rates mean. Now I come to my next topic that I wanted to say, namely, what are the implications of the Higgs mass? This is what I want to discuss next. So remember that all the masses other than the Higgs mass in the standard model are actually predicted in terms of the vacuum expectation value of the Higgs field. Remember that. But also remember that the Higgs mass itself is not predicted, okay, in the theory. The Higgs mass is actually lambda times v square, and lambda is undetermined and is actually something that now we are learning about when we actually measure Higgs mass. And in supersymmetry, this lambda is in fact related to gauge couplings, and therefore the Higgs mass is bounded, and in fact one can predict bounds. So just remember these three things. Now remember that keeping the Higgs light, as we heard today, was really razor the thread for many beyond the standard models. Either you could use symmetries to keep it light, which was supersymmetry, or let the Higgs be pseudo-Goldstone boson, which was the light composite Higgs, or remove the need for any fine-tuning by going to extra dimensions. These are all very valid options of physics beyond standard model. Now in supersymmetric theories, indeed there exist 3 Higgs bosons, rather 5 to be honest. 3 are neutral, I am talking here only of the neutral sector, and the 2 charged ones. And the lightest state, mass of the lightest state is actually bounded from above. And this is actually one sector of supersymmetry models where predictions of masses and mass bound is rather robust and insensitive to the mechanism of supersymmetry breaking. Because while supersymmetry is extremely pretty, elegant, beautiful, the breaking of supersymmetry is an extremely ugly, ununderstood idea. So if you have a prediction which is insensitive to that, we should be happy, and the Higgs mass happens to be one of these. Now the mass of our observed resonance, which is very close, and mind you, less than the upper bound. If it was on the other side, then already we would have said minimal supersymmetric standard model is ruled out, stuff like that. So already there is this fact that the mass of the resonance is below, but very close to this upper bound, actually requires, I will show you that in few plots, requires stop quarks which are quite heavy, at least one around a TeV, and hence this thing begins to get a little unnatural. Now what is meant by unnatural? That in supersymmetry, one of the great things that we do and we like is that it's the running from the high scale to the low scale which triggers the electroweak symmetry breaking. Now if this has to trigger the electroweak symmetry breaking, there is a relationship between mz, mh and mu. And this relationship, if mz, if this has to be satisfied, and if the Higgs mass is so close to the upper bound, you need to fine tune. It requires very fine cancellations, and if the mass becomes closer and closer to the upper bound, this fine tuning increases. So that is the sort of point that we all are a bit worried about. I just took, there are actually tens of plots and hundreds, if not hundreds of plots. There are many different versions of supersymmetry breaking. This particular one I have taken from some work we did with Utpal Chattopadhyay in something called stochastic superspace framework. Only thing it does, it gives a different boundary conditions. sort of justifies or some different sets of boundary conditions than are assumed in CMSSM. This is the M0 common mass at the high scale. This is the not common mass actually, but it's a large scalar mass parameter. This is the Gaugino mass parameter. And what I want to show you here is that the fact that we have the light state above 100, if you look at the masses, more or less you can say, if I take one mass 125, another at 127, I can say the within errors allowed region is 123 to 129 at best. So here what we have done is that we have plotted contours of 123 and 127, and you can see for yourself that already from the fact that the mass is rather close to the upper bound, we have ruled out small values of the scalar masses and small values of the common Gaugino mass parameters. So this is in some sense, so to say, consistent with the fact that we haven't seen these supersymmetric particles at a TeV run. Because this Higgs mass, this condition can be satisfied more or less generically only when these mass parameters are rather large. I have taken this one from a very extensive analysis by Joadi and his collaborators, and they do this analysis in something called PMSSM, which is phenomenological MSSM, and therefore the many hundred parameters that Ramesh doesn't like have been reduced, but not as much as in CMSSM, just to 5 parameters, but made sort of assumptions which are sort of physics motivated, saying that the first 2 generation quark masses are heavy, and because that is something you require even for various flavor constraints. The 3rd generation stop, you do require to keep the Higgs light, so that you delineate the two, and more or less to get a light Higgs, you need the so-called maximally mixed picture, that is the stop L and stop right. The mass eigenstate is a sort of very mixed, maximally mixed of the supersymmetric partner of TL and supersymmetric partner of TR. So this is in this maximally symmetric scenario, and this is when the supersymmetric mass scale is around 1 TeV, where all the different parameters that they vary are related to this MS in by order of factors of order of magnitude 1, which are well motivated. And what I want to show you here is that, for example, this is from the LHC results on Higgs to AA, Higgs to A to tau tau, as well as charged Higgs searches, H plus, the H plus decays, and therefore this blue region is in the region in the tangent beta MA plane, which is completely ruled out by CMS searches. This was the region that was ruled out by the LEP searches, and this blue region is the region where you can get Higgs mass between 123 and 129. So by having found a Higgs which or a boson which is not less than 123, you have said that I cannot, I'm not in this region of the parameter space for sure. And what is this? This is MA versus tangent beta. And I should also tell you that why the large tangent beta regions get ruled out so quickly by LHC searches is that the Higgs to A to tau tau decay mode is very much enhanced at large tangent beta. Also the BB production of the Higgs gets very much enhanced at large tangent beta. So these are where you had expected large rates, plus these are from flavor physics. Again, the flavor physics constants Bs to mu plus mu minus, B to S gamma, all are enhanced at large tangent beta. Large tangent beta is basically then getting ruled out. Okay, this red means it's ruled out. So what it says is that this blue region where the MA is between 200 to 500 and tangent beta is anywhere between, this whole region is sort of okay as far as the Higgs mass is concerned, and most of it is okay from B physics constraints also. On the other hand, if then the scale becomes 3 TeV, that means if we start pushing the scale because we don't see anything and the scale of the remaining quarks that you have not seen gets pushed up and up, then you would find that the region where the Higgs is this mass actually is reduced here. Okay? So what one is really saying, and at low MA, of course, the flavor physics constraint kicks in, and that region is not allowed. So all I'm trying to show you here is that we are now in a very interesting game. Okay? This is tangent beta.
No, the white of that.
The white is you don't get the Higgs mass here. You get two smaller Higgs mass. That's the way it is. And I think that has to do, in my opinion, it has to do with the assumptions they have made how MS is related to the mixing in the stop sector. Because I have no idea on this. I mean, this is not my analysis. The earlier one was my analysis where we took 127. This is Jordi's analysis, and my judgment why they get such strong results is because of the relationship between MS and AT. Because essentially this is controlled by the mixing in the stop sector. And they have related mu, the mu H1 H2 term, mu to MS in some ways, and to M2 and M1. So I think this is due to that. But what I find also very interesting is that what is the maximal mass that you expect for the Higgs in different scenarios, and this is the, and they do a parameter scan over a space which is still allowed by LHC. So all the other parameters I really have not written down here, and what they show is that in CMS, in M-SUGRA for example, this is the 123, this is 129, so what you can say really is that as MS values of about 800 to 1000 are ruled out. On the other hand, if you are in a more restricted framework, because this is a PMSSM, if you are in AMSB or GMSB, you actually find that the limits go higher. Now at 18 TeV, at 14 TeV, you should be able to see signals if there are squarks and gluinos at this scale. So we have to see. But this tells you how that one mass is ruling out a whole lot of things that I would have otherwise liked to motivate from many different theoretical arguments. So I think nothing like experimental information ever. So the order of the day for actually for supersymmetry is to look for the light stop. This is indeed what the results tomorrow will be presented at that Ramesh was talking about. And there are many phenomenological and experimental investigations. Right now the CMS limit on stop is there is a strong exclusion between 300 to 500 GeV, more or less, which is the edge of the reach of 8 TeV LHC. You cannot do better than that at 8 TeV LHC now. Atlas excludes a little stronger, but they are based on more assumptions. I should also make a point here that these masses of the stops are still just about okay with generating baryon asymmetry in the universe. Just about okay. With this mass of the Higgs, this mass of the stop, they're just, you can do it if it works. In NMSSM though, not in MSSM. Okay. So, now I come to the issue of, I told you that I am looking at, I have shown you one thing, how the one thing, namely a theoretical upper bound on the Higgs mass, comparing it with the measured value of the mass of the resonance, has given us a lot of constraint on, for example, supersymmetric models and a lot of pointers in the model building. And of course, we have to always connect it also with the flavor physics constraints, and they are all sort of gone in most of the analysis that people have been doing. Now, the other point that I want to remind you is that, for example, let me go back to December 2011, before the announcement of the resonance was made, but when some excess was reported. So in 2011, if one would have asked, what is it that we do know in terms of bounds on the Higgs mass, we would have said, we have indirect bounds which come from the electroweak precision tests, and we have theoretical bounds which come from quantum corrections to the self-coupling lambda. Better known in theoretical bounds, better known as triviality bounds and vacuum stability bounds. So let me look at these two. So the indirect bounds which came from the lab measurements were very simple. They simply said that you have made precision measurements of a whole lot of observables, make a fit in the standard model. When you make a fit in the standard model, every quantity that you predict in the standard model depends on the Higgs mass. So calculate the chi-square of your fit. If the minimum of the chi-square actually is achieved at a non-zero value of the Higgs mass, This was indeed what was mentioned earlier in this morning, was then the proof of the existence of the Higgs, so to say, because otherwise I would have got, if I would have got a fit, I would have not got a fit at minimum at some value, that would have been already pretty bad. But indeed we got the fit here. That was the big success of the standard model as tested at the at LEP. And then now you say, I say that I put an upper limit from the indirect measurements when the chi-square changes by 4 units, that's a 2 sigma limit on my Higgs mass. And on top of it are of course direct search bounds. These were from Tevatron, these were from LEP. So in December 2011, if you wish, this was the region where if the standard model was right, Higgs should lie. And this is coming from an indirect source. Another one was corrections to the radiative corrections to the W and top mass and the accurate measurement. This also came in February, in fact, and a very good measurement from the Tevatron of the W mass, and which told that again the only region that was kind of left was this very small green slither. So this is what we would have known from indirect loop contributions. And now the experiments have just found it just there. So this of course is something that got us all jumping to say, yes, indeed the standard model is right. This is one of the more important reasons why we say that indeed this is very likely to be the standard model Higgs, even if we have these issues about what are the precise uncertainties in the rates of production, in the calculations of the decay rates. This is the fact which tells us that yes, what we are seeing is most likely a standard model thing. I want to remind you that the allowed Higgs mass in these indirect fits, in fact, change if one goes away from the standard model. And in fact, myself included, many of the theorists always were worried that we won't find the Higgs in this small slither, and we were trying to think that this will give me the indication of physics beyond standard model. So we were cooking up explanations of very generic beyond standard model physics, which would actually allow the Higgs to be heavier than that small range. And in fact, now we find that many of these BSM scenarios are not required, but more than that, some are now getting ruled out, and that is the one that I want to talk to you about. One of the example is a model with 4th sequential generation with single Higgs doublet. Actually, that was a very, how should I say, innocent extension. And I thought, why not? I mean, this will help me explain the baryon symmetry in the universe quite nicely, will give me sources of additional CP violation. Maybe I have something in the B physics which requires the 4th generation. There has been a lot of theoretical investigations on that issue too. And now comes the very interesting, phenomenology that happened just with the Higgs. And that to me shows the strength of the whole information that we have got. So this 4th sequential generation was actually very popular, and in fact I have already given you the reasons. And what happens is that for values of Higgs greater than 2 MW, the GG to Higgs to WW rates get enhanced by a huge amount. So that would be a telltale signature of the 4th generation, or on the other hand, a very easy way of ruling it out. And in fact, that is what happened even before. This was a plot from July 2001 or August 2011, where in fact the Atlas collaboration already, this is 35 inverse pico-1 data, the first piece of data, they ruled out a 4th generation Higgs in the mass range from 124 to 600 GeV at one go, because the enhancement in the rate that was expected for 4th generation was not seen. So in fact, at that time we looked around at this piece of data, and we said that actually in the SM4, a heavy Higgs greater than 600 GeV is in fact consistent with electroweak perturbative test. So we said, fine, now let me look at what are the implications of such a heavy Higgs. And indeed, we did this small exercise, and we said that if there is a Higgs greater than 600 GeV, then you are allowed a 4th generation mass difference MT prime minus MB prime greater than MW. Whereas before this, people always used to say that electroweak perturbative test, because the T parameter, the rho parameter is very close to 1, does not allow large mass splittings between the 4th generation fermion. That was our folklore. Now, and that was, we just found that if the Higgs is heavier than 600 GeV, just the additional contribution that the Higgs made to the S and T allowed you to have a splitting in the 4th generation doublet which is greater than MW. So we'll say, so what? Why this is so important? This is important because earlier most of the search strategies where that T prime does not go into a B prime W, but T prime goes to something else. So which means that this kind of interplay, just because based on this one piece of information, is very interesting. But that is just at the level of being interesting. Now, at this point, we didn't have any information about 125 GeV Higgs, but the minute this was announced, actually, my friend Joadi, I found a very interesting thing, and this I want to share with you. What you realize is that the Higgs to gamma gamma has interference effects which calculate from loops between W loops of T prime, B prime and L prime, and in fact where the Higgs to WW, GG to Higgs to WW increases because of the 4th generation, Higgs to gamma gamma decreases because of the 4th generation fermions. And this simply happens because of the destructive interference between W and the T prime, B prime and L prime, which does not happen for glue. And in fact, what they found, if you took the naive expectation for Higgs to gamma gamma, it was still allowed 125 GeV Higgs because of the interplay between the increase in the rate of GG to Higgs and decrease in the rate to Higgs to gamma gamma, in the end was just about on the same level as the standard model. So they said, okay, 4th generation is still alive. But what they noticed, and that was very important, that when you do exact next to leading order electroweak corrections, which were done by Denner et al., they implemented them and they found that the Higgs to gamma gamma is suppressed much more than people thought, which meant that the very fact that you have seen a Higgs at a boson at 125 GeV, if you interpret that as the Higgs, the sequential 4th generation scenario is really, with a single Higgs doublet, is really buried by a large sigma. So this is the strength, as far as I can see, of this one piece of information that we get. This is independent of what is the mass of the 4th generation, okay, because these are loops that I'm computing. And I like this particular thing. Yes, sir. Yeah. Glue to Higgs to WW. Oh, I mean just this. No, sorry. I mean the enhancement is because of glue to Higgs. Higgs to WW, nothing much happens if I have a single Higgs doublet. Now this is where people start playing. They try to see whether this is still allowed with 2 Higgs doublets, where I play with Higgs to WW couplings and then hence 2 Higgs to gamma gamma coupling. So that's actually the game that people try to play now to see whether 4th generation is still allowed. So in fact with Srihari here, we decided to do something. Then we said if a sequential, because what is happening here? The reason that this is happening is because you have Dirac fermions which are flowing in the loop and the contribution does not decouple fast enough. Now if you have vector-like fermions, then these contributions, loop contributions, in fact decouple much early, and therefore question is, are you allowed any space for additional vector-like fermions, though the sequential Dirac fermions seem to be ruled out. So what we did is that we have added to the standard model vector-like a doublet which is vector-like under SU2L cross U1. We write down a vector-like mass term, realize that this mass term has now nothing to do with the Higgs. This is a different, origin of this mass term is also different, and which is what allows this guy to decouple fast. And then in fact Sri has done this, this is very much a work in preparation. So what we now see is that as I already said this, that compared to the 4th generation fermion, they are decoupling faster, but as a result of that they are also constrained when I look at the precision constraint and look at T and U. So S and T here are plotted as a function of this mass of the heavy quark. So as you see that the measurements on the S and T will already allow only certain large values of the MQ, And now you have to ask a question, what happens to Higgs to gamma gamma for the values of MQ that are still allowed by the precision measurements. And indeed, what we see here is that the signal strength, the same mu hat that I showed you earlier, how does this mu hat change as a function of the mass of the quark depending on the quantum numbers of the quark. You see that for some quantum numbers, indeed, it is always less than, it is very low, much less than 1. In many cases, it sort of goes to a constant, hugging about 2. So what one is now saying is that by this combined analysis, you can sort of do a model independent way, depending on the quantum numbers of these vector-like fermions, what is still allowed by the different piece of data and what is not ruled out. Now these quantum numbers of these fermions actually depend on the particular realization in a warped extra dimensional model. The different realizations, different embeddings give rise to different quantum numbers. So there is a completely different model building that one can link to this, but this is a kind of information that you can already gain. Now I come to so I have tried to give you some sense of how the combination, first how the Higgs mass information leads to non-trivial constraints. Then I have tried to give you my own perception about the uncertainties in the various rates that are being quoted, how they should be treated. Thirdly, by not thinking about it, I have also, because those objections that I am taking are sort of minor fluctuations over the major result, I have tried to discuss how using this information on the mass and the observed rates, we can already rule out a large chunk of simple-minded, nice BSM physics that we had thought would exist. And I forgot to mention one thing, is that what is nice about these plots is they will tell me that because I'm putting the constraints on the quarks from two different sectors, now if this is not followed by, this is very much in the reach of 8 TeV machine and for 13 TeV machine. So if these are the right explanations, we should find these weird objects in the current collider searches because they get produced by strong interactions. If they are coming from, and most of the time you get large effects when they are strongly interacting fermions. The electroweak fermions, just the leptons, usually don't contribute too much to the loop. So this is something that can be falsified also. So this is sort of the direction in which I think sort of model independent phenomenology can go, and which is the game that I think we need to take up. Now I want to take a slightly more theoretical issue, namely the stability bounds. And I want to point out one more interesting aspect of the value of the Higgs mass that we have observed. And this observation that I'm going to tell you now comes from a very nice work by Giudice, Strumia, and a few other collaborators, De Grassi and et al. Now what is this? If you remember that all the couplings run, I have RGs, and the effects of the fermions on the running of the self-coupling lambda actually changes it, and it changes the value of the lambda, and since MH is related to lambda of at scale V, I showed you, MH was lambda V square, M squared H. So once I know the value of MH, I know lambda at the electroweak scale, I run it, and in fact, because of the large effect of the fermions in the loop, lambda will become negative at a certain scale. So I start running it, I run it, and I start at lambda V at the electroweak scale, and the running will take it actually to lower and lower values, and in fact, if MH is not large enough, lambda could turn negative at a certain scale, and the potential will then become unbounded from below. So therefore, this then says that if I want to avoid the unboundedness of the potential up to the Planck scale, if I demand that lambda doesn't become 0 all the way up to the Planck scale, then I need my MH to be large enough. And therefore, you find that there is a bound on the Higgs mass, which is a lower bound. And for all of us, many of us in the audience here, I'm sure, we always used to worry about the upper bound which came from perturbativity, which came from triviality. And this was something in single Higgs doublet model, this always works. But now, the beauty is, and that is actually something that is, I think, a very, very interesting observation, So I want to try and show you that when we found that I will show you in a plot in a minute, and you will see that because the mass values were rather small, one needed a very accurate calculation of these vacuum stability bounds. And I should also point out, since this is because of the effects of the fermions on the running, and the top is the dominant fermion which affects the running of the Higgs coupling, these limits critically depend on the mass of the top in ms bar. Okay? And the state-of-the-art calculation was first done in 2009 by Giudice et al. And I am showing you the results of this computation. So this is much before December 2011. So these were the different bounds that they had got with this accurate calculation, and they had said that this stability bound meant that the Higgs mass should be above this line here, okay? And depending on whether you had absolute stability, whether you had finite temperature metastability, whether you required metastability at 0 temperature, you had a range here, okay? Now since this range was rather large, and then LHC in first go removed all this junk, and then it said that now what has happened, the value that we have got is very close to this line here. It is so close to this line that people needed to extend the accuracy of the calculation to be able to draw a conclusion whether lambda is really becoming 0 for this value at m Planck or m Planck less than 0. That was actually the exercise that de Grassi and Giudice took upon, and they did a complete NNLO analysis. As I said, this was really a major theoretical exercise. This I want to tell, actually, I hope the students at the back get this sense. I've been mentioning again and again the importance of high precision calculations that have played, and these calculations have taken years to do. So the community has sort of prepared for years in advance by doing these calculations, and now they are paying dividend. So here what they did is that they did this NNLO analysis, and what they showed is that where does the Higgs coupling really become 0? This is the running. That depends, for the Higgs mass of 125 GeV, really depends on the top mass. Okay? And they took the error on the top mass. So now here you see, if the top mass is 171, the thing will become 0 at 10 to the 14. If the top mass is 175, it will become 0 at 10 to the 8, for example. All right, for 125 GeV Higgs. What it says now, that the correct knowledge of m top and accurate knowledge of m Higgs is necessary for me to be able to conclude where does lambda become 0. Because now this is the known piece of information that I have. At this point I'm not putting in my ideas as to what scale can I live with this 0 value of lambda or not. We are asking a question, where does this lambda become 0? And their analysis was, they took the error on the top mass, pole mass, that was from the numbers that Mariana presented, and they claimed that a Higgs mass less than 126 GeV, the vacuum stability of the standard model all the way to the Planck scale, it's excluded at 98% level, confidence level, which means that if the Higgs mass is as small as 125, and now realize that this is log scale. So every 1 GeV in the Higgs mass corresponds to, I showed you already that, it corresponds to large number of orders of magnitude in the lambda, at which small lambda, the self-coupling becomes 0. So knowledge, correct, accurate knowledge of m top and m Higgs is really quite important. And at this point, it's not theorist anymore. Theorists have done their job of calculations quite well here. So here what we really need is, and now therefore, this is what we need to understand. And there was a very nice paper by Sven Mock and company, where they said that instead of taking this 0.7 GeV error in the top mass, I do not want to go into the discussions of that, but it was already clear from one of the plots that Mariana showed that if I take the error to be given by the cross-section measurements, then it's about 4.5 GeV. The cross-section curves where the measured cross-section matches with, okay, I mean, these people did a much more accurate job, so I'm not going to be able to cover that now. So what they estimated is that according to them, the pole mass is 173.3 plus minus 2.8 GeV, not the 0.7 GeV. And now if you say that the error is 2.8 GeV, then indeed you find that the vacuum stability constraint means that MS should be greater than 129.4 plus minus 5.6 GeV. So voila, we may be still okay. We may be still okay or not okay depending on how you look like it. What I find that this kind of correct knowledge of top mass will then be instrumental in my trying to tell whether there is new physics somewhere at 10 to the 14. Maybe I have leptogenesis. Maybe there is a new physics at 10 to the 14 GeV, and maybe this is my only chance of seeing it in the laboratory measurement. So I personally think this is an extremely interesting measurement, and in fact what I like in this paper by Mock and Joadi is they show is that supposing we assume that the Higgs mass central value remains where it is, and this is the central value, then at the present tevatron and LHC measurements together can in fact constrain it, assuming the top mass measurement can constrain it to this ellipse. But if I go to ILC, where actually I can measure the top mass from threshold scans free from all theoretical ambiguities and the ambiguities which come from fragmentation and hydronization, indeed we will be able to locate in a very narrow range, and then we can tell at what scale of lambda does indeed small lambda become 0. So I personally think this is a very, very interesting observation. So this tells you that just one number really can teach us a lot. Now, having sort of made this point, I want to go to the next step, and how do I determine the spin and CP quantum numbers of this resonance that we have found. So that's our next point, and hopefully the last point. Okay. So I wrote this before, you remember. If it is standard model, for example, I told you that I'm going to be looking at only Higgs to ZZ and Higgs to WW, excuse me, and also Higgs to gamma gamma and glue to Higgs. So only vector boson vertices, because those are the only ones on which we have very reasonable information right now. So if A is 1, B is 0 and C is 0, that's the standard model Higgs boson. B normally is a CP even term, so even in standard model it will come as higher order corrections. But C not equal to 0 would mean that I have a CP odd contamination in the state. So what we would like to do is, can we get information about whether I can discriminate between a hypothesis where A is 1 and C is 0, or A is 0 and C is 1. Can I at least discriminate between these two hypotheses at the present stage of the game? If I want a determination of B and C, clearly I need a ILC. I need a E plus E minus measurement with polarized beams and the whole shebang. Right now you ask a very simple question, can I just distinguish, this is using just to Higgs to ZZ. Now what it means is that, or Higgs to WW, which means that I'm not relating it also to the fact that the Higgs to gamma gamma coupling and the Higgs to ZZ coupling relative rates are consistent with standard model, and hence my Higgs to ZZ is CP even. I'm not going to use that information. So therefore, I would allow my C to be as large as I wish it to be. That there's something that is coming from higher order corrections, it's some loopy facts. I will say, okay, there's CP violation, C can be of order 1. So the rates of Higgs to ZZ, even with these operators, can be large. And now I ask a question, are there any distributions, kinematical distributions, that will distinguish between A being 1, C equal to 0, A equal to 0, C equal to 1. Actually, this is something that many of us, I have already said, so I will leave it. That the substantial production already meant that that I will leave, because I am just talking against it. And now basically the idea was that one looks at the kinematic distributions of the decay products of the ZZ. A long time back there was work done by Zervas, Miller and Wilheitner Choi, and little bit after that, but still quite a few years back, we had done some work on this. And what we had shown is that you take Higgs to ZZ and you look at the distribution of the invariant mass of the Z star, and you will see that in the case of standard model you expect this, for example, whereas for the spin 2 you would expect this. For a CP odd state you would expect the distribution to be this. For a CP even state you would expect the distribution to be this. So you say, voila, measure this distribution, you will have some information whether A is equal to 1 or C is equal to 1. This is the shape of the distribution. In fact, In fact, we also did something more, and we had shown that the distribution in the angle between the planes of the two fermions, Z going to L plus L minus, another Z going to L plus L minus, you look at azimuthal angle, and that will also be different depending on the values of the A, B and C. In fact, if it's pure CP odd, you would expect this. If it's the standard model, you would expect this. So it's clear, you can actually measure this. But again, these kinds of measurements, at least in our simplicity and sort of naivety of theorists, we had thought that this will be a measurement that will come at high luminosity. And in fact, what is now used as MELA, and what you saw today, the analysis, results of the analysis, which I'm sure Kajari showed you, indeed says that by using all these distributions simultaneously, you are able to see that the distributions seem to be consistent with what is expected from a CP even case at about 2.8 sigma, and the CP odd, it seems to be discriminated at the level of about 1.8 sigma or 2 sigma. So which means we are already getting there. And this is the statement that I was making, that this is now here, see what you are using here. Here you are using only Higgs to ZG, just by itself. So that is actually a very useful thing. But now recently, there has been a paper on the web, Angular Plane et al. Just yesterday or 2 days back, and an analysis that we have been doing with one of my students, Kirti Manmohan, Abdel Jawadi and Bruce Bellado. And what we now say, we are actually going one step further. We are saying, I don't even want to look at the decay. I want to look at the production, because all I need is the Higgs BB vertex. So you look at the vector boson production, so WW or the ZZ comes, produces a Higgs, and there are two jets which are going. You look at the rapidity difference between these two jets, and it is common wisdom that the vector boson fusion for the standard model, the rapidity gap between the forward and backward jets is very large. Now, what we found, and what Plane and Angular etc. also found, is the following. What I show you here is the distribution in the rapidity difference between the two jets. For the standard model, I'm sorry for the poor quality of this plot, because this is still very much a work in progress. For standard model, we expect this. For C equal to 1 or B equal to 1 and A equal to 0, I expect something like this. So completely different distributions. Not even that, even more interesting. For spin 2, whenever there is more energy and momentum which is pushing into the vertex, that's all I need. For spin 2, exactly the same. Which means you don't even care about the decay. You only care about, in the vector boson fusion, what is the jet distribution between the delta eta between these two. And the fact that we have seen a vector boson fusion signal which use the rapidity gap as a selection criterion already seems to indicate another kind of proof that maybe we have a spin even case. But this is the one way you can try to differentiate and try to study more, even with the low statistic sample. So I think I have kind of run out of steam now. So the next part of the talk is something that Vishwarup is sure to cover. But I will make only one point which I want to make, and this is this which I already said in words, that I already showed you two different interesting properties that 125 GeV Higgs has. It is just above or close to the SUSY bound. It is just near the vacuum stability bound, and now it also happens to have a value such that all the branching ratios are sizable. If that were not the case, I couldn't do this spin analysis, okay, apart from our jet channel, okay. The jet channel we could still do, because vector boson fusion would have still happened, but I think the ZZ channel would not have happened, for example. So this is indeed a very interesting mass value. Now I am going to leave out the rest part, which I am very, very sure that Vishwarup will cover. So this is the part which I am going to now not cover. But what I want to show you, and the only one thing, that in these general fits that people have been doing, and even CMS has just done a general fit, and in spite of the fact that one says that all the branching ratios are consistent with standard model, there is still room for a possibility that the Higgs just has invisible decay products. That is still allowed. That is still allowed by all the most, sort of recent fits after HCP. I think CMS allows something like 60% branching ratio in a general fit into invisible channel. Now, such an invisibly decaying Higgs for a E plus E minus machine is no problem. But for a hadronic collider, that's an issue. How do you look for such an invisible Higgs? You can also ask a question, are there theories which predict it? And sure enough, there are many theories. One of them is supersymmetry. And in fact, this is a paper which we had written again in December last year, where we had shown that consistent with all the experimental information that was available, we did a parameter scan and we found that there can be, these green regions are always allowed. So you see that you can have considerable 0.2, 0.3, 0.4, see 40% invisible Higgs branching ratio. So one of the things that people are doing is how to look for such an invisible Higgs, and this way, even if the remaining supersymmetric particles are beyond LHC's reach, we might see this through its effect on these products. For example, if it's a pair of neutrinos which is making it light neutrinos which are making the Higgs invisible, the collider searches will not show it. So therefore, by looking at things like this, may be another way of probing physics beyond standard model. I would also like to point out for those of my friends who like to make models to enhance the Higgs to gamma-gamma branching ratios, that most of the models which do it have to have colored particles, but now the same colored particles have to run in the loops to correct the Higgs potential, and again can create problems by making lambda negative. So if you try to put the tarpaulin down in one place, it may come up in another place. So one needs, again, what I find amazing and beautiful is the interconnections that all these things have, they have to have, and therefore we can now study what is, I think for the first time we will be studying something beyond what standard model tells. Okay, we have chance of studying, doing some, in my mind, something that we didn't expect. I find this one particular plot which was made by Ellis and you very nice, because I told you we want to know whether the Higgs is a Higgs, whether the boson is a Higgs. And what is it based on? They actually make a fit, and what they show for the first time, I think, is that the coupling is really seems to be proportional to the masses. So that to me is a really sort of pretty plot. All right? I don't know whether it is the Higgs. It is a Higgs. I said it's a Higgs. Huh? Yeah, there are many things on it. But for the first time you have a plot like this, that's all. For me it's interesting that you have a plot, but it is a Higgs, if at all. It's far from being the Higgs, my dear. So, is this then the end? And I like to think that it's not even the beginning of the end. I think, if at all, is the end of the beginning which happened in 1967. So, I already said this, that the mass of the observed state is very interesting from many points of view. It's just small enough to keep us still thinking of a mechanism like SUSY to stabilize it, but which is making it not so easy. It's just large enough to make us wonder whether SM is the only thing all the way to the Planck scale. Now this is an observation which makes us wonder, which is different from our own aesthetic preferences. And it's a unique value where the resonance decays into almost all the final states very substantially. Already many BSM ideas are constrained very strongly. The first glimpse seems completely consistent with the standard model, but I think we need to be patient and hope that we can get a look into the BSM land through the properties of this Higgs. Coupling determination and the CP determination are the order of the day, and the spin. Important to understand how we should treat the systematic theory uncertainties when we are doing coupling determinations. Because for example, in those, even on the logarithmic scale, the plots that are made assume that these guys are actually ratios of cross sections. And as I told you, I don't have any reason to say that they are only estimators of ratios of cross sections. And a small change there can make a big change. So that's just all indicating. So in any case, I think the days of the standard model are coming to an end in some sense. We hope that it will be the case of the king is dead, long live the king. Which the new king is, we don't know. Many of us, me including, had hoped and still hope that supersymmetry will be the next king, but we don't seem to find it so far. But the adventure is just beginning. And just like the gauge principle and unitarity really guided us through, that's why I began in 1967. Just like they guided us through, maybe it is the light mass of the scalar that we have found is going to guide us through to the next stage. And I believe we are all hoping and wishing that we would get a peek at the BSM land through the window of the measurement of the properties of the Higgs, whether that happens at LHC, SLHC, ILC, click, whatever. Exciting days are ahead for sure, and I think this is it. Thank you very much.
Yeah, I'm sure you have a lot of questions. Yes.
Bound, is there a lower bound for MH from this potential? Not.
Sorry, I have the mic.
There was a lower bound for the Higgs mass
Huh?
from saying that the potential shouldn't turn around.
Correct.
That assumes the standard model all the way to M Planck.
Well, what it does is that it assumes there is no other further particle content.
Right. So if you modify it with supersymmetry or
But
something,
that's
what-
exactly what I tried to say. That now if I modify it with that was the point that I was trying to make in that paper by Rees. That what you have to do is that it has implications. In general, in the past, we used to forget about the contributions coming from the additional particles in the loop. Now, second, if they are, what happens is that if I just look at tau's or something contributing to it, we are still safe with the current Higgs mass. But because they don't add the colored particles which start making life very difficult.
no, so it's
Which would then tell me that the vacuum stability will tell me that there should be new physics below a certain scale by hand, more or less by construction. And then if I have not seen the particles, those particles at the LHC, then that explanation is wrong. Am I making sense? From your face it doesn't look like. No, all I mean is that this will turn negative at some point, right? Now when it turns negative, you say that there must be new physics before that scale. That's what we are going to argue. Now, if that scale at which it turns negative is too low, then I should find the evidence for those particles that are making it negative at that low scale, at the LHC. If I don't find them any evidence for them at the LHC, then the whole thing is wrong. It's in my head and it's not correct. Am I making sense now?
Madam, in your talk, and ratios of different quantities. So I understand this is done to cancel out uncertainties which you have both for theoretical and experimental measurements. Now, when you talk about this double ratio kind of thing, what are the exact quantities you address to?
Okay, I will tell you why. Why I am taking ratios of ratios.
Yeah.
The ratios of ratios are for the following. Supposing I look at glue, that was actually that was a sort of related to a question that Sri had asked. You look at glue to Higgs to ZZ,
Yeah.
and you look at glue to Higgs to gamma. Now, in the glue to Higgs, if there is modification at the top loop level, if there is modification, so whether there is modification at the decay level or whether there is modification at the production level. So if I take the ratios like this, then I isolate. So therefore I say, let me forget about glue to Higgs production. I may have not understood my QCD scale uncertainties. My answer will be independent of that ignorance.
Okay.
Then I would get information about Higgs to ZZ coupling to Higgs to gamma coupling through the things that are flowing in the loop. If I take vector boson fusion production going to gamma, Higgs to glue going to gamma, now I can isolate the physics that affects Higgs to gamma. Something like this.
I see.
There was actually a very nice analysis that was done by Joadi on this, which I thought was very, very nice. And that's perhaps the only analysis where I know it has been done, which is makes this point and which is good.
Okay. Thank you.
Any more questions? Okay, if there are no questions, let's thank the speaker.